Good afternoon, friends. I welcome again you in the next session of our normal distribution and its application along with its property. In the previous session, you have enjoyed with respected Professor Ashok Shah. They have discussed already some property and its application with the long history of the normal distribution, which is one of the most applicant distribution. Let us again see some more properties with having some flashback of the previous session, and we will again see some application of normal distribution again along with it. So let us start our journey. Here again, history of the normal distribution. The most important continuous probability distribution used in entire field of statistics is the normal distribution, and the founder was respected Carl Friedrich Gauss during 1777 to 1855. Again, the normal distribution is often referred to as the Gaussian distribution in honor of Carl Friedrich Gauss. Here this fellow has studied some distribution of errors. So that's why this normal distribution is again also called as a distribution of error, that we will see by one activity afterwards. Here again, you know the normal density. The normal is a theoretical distribution specified by its two parameters, respectively mean mu and sigma square. Here variable x can take value minus infinitive to plus infinitive, and PDF is given as you can see 1 upon root 2 pi sigma square multiplied by e raised to minus x minus mu square divided by 2 sigma square. Now the normal distribution with mean mu and variance sigma square may be also denoted by the symbol n for normal, mean mu, and sigma square is variance. Here the PDF fx greater than 0 for all value of x, and the integration of this PDF fx in the range minus infinitive to plus infinitive is equal to 1, and the parameters again mu and sigma of the normal distribution are the mean and standard deviation of the distribution respectively. Here let us discuss some properties. Symmetrical property means the normal curve is a symmetric. Again its mean it is more clarified by this pictorial view. Here you can see that mean, median and mode are equal and located at the same point. Now normal curve is again symmetrical with two halves identical. Here you can see the tail parts also, it is not touching the x-axis but it is quite asymptote. And here theoretically the curve ends to minus infinitive to plus infinitive. So that was that. Again next property is bell shaped, already discussed. Here the curve of the normal distribution is having a bell shaped curve. Similarly, tails are asymptotic. It means that they never touch the x-axis. You can see this figure. They never touch the x-axis. Okay, next property was mean and median and mode are equal. Let us have an example. Here this example is for final grades in social statistics of 1200 students during 1983 to 1993. Here in the first column midpoint scores are given, which are 40 up to 100, and for our convenience I have included the frequency bar chart here. and after the subsequent two columns you can see the frequency and cumulative frequency also. Now problem is how to check the normality. It means that how to decide whether the data is following normal distribution or not. Here, for this checking, to overcome this question, we will have to initially examine two things. First is look at the shape illustrated by the bar chart or histogram. So here you can see the bar chart. The bar chart is again having the shape like bell shape. It is again a one property of normal distribution. So it is enough to say that your data is following normal distribution. Again, the second point is to calculate the mean, median and mode. If mean, median and mode are equivalent, means are somewhat same, then you can say that the data is following again a normal distribution. Here in our case, mean is 70.07, median is 70 and mode is also 70. So they are approximately same. So it is quite enough to conclude that our data is following the normal distribution. Again, here since all three are equal and it is reflected in the bar graph, we can assume that again the data is normally distributed. Okay, that we have already discussed. Now next is also since the median is approximately equal to the mean, so it is quite enough to conclude that our distribution is symmetrical, means the two halves are identical, or if you fold your curve from mean, it will give you a mirror image of each other. Again, from the pictorial view, it is more clear that mean, median and mode are equal, curve has bell shape and asymptotic to the x-axis, never touches the x-axis. Okay, this property is unimodal, means our distribution have only one mode, that you can see in the figure A. So in case of normal distribution, here the curve has only one peak point, means only one mode, that you know. And in either of the cases, means in the non-normal condition, you may have bimodal as well as trimodal curve, means your curve may be having two peak points in the curve and also three peak points in the curve in case of non-normal data. So it is now clear that in the case of normal distribution there will be only one mode, means this distribution is unimodal, means have only one mode. Okay, next is total area under the normal probability curve is 1. Again, the ordinate at the mean of the distribution divides the total area under the normal curve into two equal parts. Let us see. Here, from the ordinate of mean, total area is divided into two equal parts, two identical parts, or you can say it generates mirror image from the mean. So, if the total area under the normal probability curve is 1, each separated area from mean will have probability 0.5, 0.5 each. Now next, let us see some descriptive measures for normal distribution. Here, mean is equal to x bar or mu and variance is denoted by mu2 or sigma square. Friends, you know the formula for mean and variance respectively, right? Now third central moment, mu3 is always 0 for normal distribution, as well as fourth central moment, mu4 is equivalent to 3 sigma raised to 4 or is equivalent to 3 mu2 square, because mu2 is equal to sigma square. You can see this is the variance, notation for variance. Now again let us see the skewness. skewness beta 1 is equal to mu 3 square divided by mu 2 cube, that you know the formula, which is 0 in the case of normal distribution. So you will be having the normal curve as described in this figure extremely left, right? So in case of normal curve, you will be having the first figure from left. Now if your skewness beta 1 will be greater than 0, in that case you might be having the positive skewed data. Positive skewed data means your extreme right tail will be quite longer than that of left tail of your curve. So in that case, most of the data will be situated or located, or you can say concentrated, upon the left part of your curve. Similarly, if your beta 1 is having this value less than 0, means you will be having the negative skewed data. So in case of negative skewed data, your left tail of the curve will be quite longer than that of right hand side of tail. So in the case of negative skewed data, total area will be more concentrated upon the right hand side of the curve. So in case of normal curve, most of the data will be centralized around the mean, you can say. Or it is very easy to see from these figures. Now next, kurtosis. Next is kurtosis. So kurtosis is beta 2 is equal to mu 4 upon mu 2 square, that you know in case of normal distribution it becomes is equal to 3. So you can see the green part, mesokurtic curve. So you can have this type of curve whenever your beta 2 will be is equal to 3. If your beta 2 will be less than 3, then you will be having the platykurtic curve. You can see the figure, friends. And in case of beta 2 greater than 3, you will be having leptokurtic curve. So here you can see the general forms of kurtosis. So wherever you will be having platykurtic curve, your data will be quite skewed with respect to the leptokurtic or mesokurtic curve. Whenever you will be having the leptokurtic curve, the thickness of the curve will be quite taller, you can say that, and in that case you may have less skewed data, means the spreadness of the curve will be less than that of platykurtic curve. Okay, now let us see the quartiles property. The quartiles Q1 and Q3 are equidistant from the median. It means that the distance Q2 minus Q1 is equal to distance Q3 minus Q2. Or in either case, means if your data is following not normal distribution, you may be having positive skewed data as well as negative skewed data. It is given in the figure that your quartile Q2 will be quite near about Q1 in the case of positive skewed data. Wherever at the other hand, if you will be having negative skewed data, your Q2 will be quite near about Q3. It means that in case of non-normal data, the distance of Q1 and Q3 never be same about Q2. Okay, now it is asymptotic to the baseline x-axis on its either sides that we have already discussed, and as the distance of the curve from the mean increases, the curve comes closer and closer to the x-axis but never touches it. Keep it in mind that, but never touches the x-axis. Let us see this figure here. See these tail parts. So here the tail parts are quite far away from the median location. So this tail parts curve is quite near about the x-axis. You can see here nearby the mean, the curve part is quite far away from this x-axis. Clear that? Okay, next here remember this PDF because we are going to use it. Okay, so in this PDF the power of this exponent have negative sign, right? So if we want to maximize this function of x, you will have to maximize this total exponent part, and the power of this exponent will be maximized at 0 because here there is minus sign, right? So e raised to 0 will be 1, but when it is going to be happen? So if you are taking x is equal to mu, at that time you will be having e raised to minus mu whole square divided by 2 sigma square. It is going to be 0, means the power of this exponent is going to be 0. Now e raised to 0 becomes 1, and you are having your PDF at maximum is nothing but 1 upon root 2 pi sigma, or you can say that 1 upon sigma into root 2 pi. If you are taking out this sigma square from the square root, it becomes sigma. It is quite obvious. I repeat, okay, this power is negative and we want to maximize this function of fx. Means here whenever you will be taking x is equal to mu, then the power of this exponent becomes 0 and e raised to 0 is equal to 1. So again we are having this function, maximize of this function, where 1 upon root 2 pi sigma square in square root, or you can say 1 upon sigma root 2 pi if you are taking outside this sigma square. Okay, now thus the maximum value of fx is inversely proportional to the standard deviation. Let us see here, because the standard deviation sigma is in the denominator, this fx is inversely proportional to that standard deviation sigma. Okay, now it means for small values of sigma, PDF means fx increases, and it means the curve has a sharp peak, and for larger values of the sigma, fx decreases. It means the curve is going to be more flatten and flatten. Let us see this using this figure. Here the standard deviation is small, so the curve has more peakness, and in either case this sigma is quite large, means the spreadness of the curve is going to be high. It means your curve is becoming more and more flattened. Okay, here additive or reproductive property. Here the sum of independent normal variates is also a normal variate. It means that if you have n independent normal variates, say x1, x2 up to x small n, and if you are adding this all n independent variates, so this is also following the normal distribution. Here the mean of that sum of all independent normal variates will becomes the sum of corresponding variates mean, means mu1, mu2 up to mu n, all are the individual means for independent normal variates. So just add up, means just have a summation of that all means. Similarly the variance is also a variance added by all that individual variances, means sigma 1 square, sigma 2 square up to sigma n square. Okay, now let us see area property, which has been already discussed in the previous session by respected Professor Soksha sir. Let us see. About 68.26% of the area under the graph is within one standard deviation of the mean. It means the range is mu plus or minus sigma. Let us see. Here from this figure, within one standard deviation of the sigma from mean mu, we are getting almost 68% observations in this area under the curve. Next is about 95.44% of the area under the graph is within 2 standard deviation of the mean. It means the range mu plus or minus 2 sigma. Let us see. Here, within the range mu plus or minus 2 sigma from mean, almost 95% of the observation will be following within this range. Similarly, about 99.72% of the data will be fall within mu plus or minus 3 sigma range. You can see here about almost all data will be covered within 3 sigma ranges. Hence, for practical purposes, the range mu plus or minus 3 sigma, which covers the entire area, almost all area, which is taken as 1, because rest of the all observations may be negligible. So this mu plus or minus 3 sigma property, this area property, I think that there must be reason that rest of all the theories in the statistics has been developed under assumption that the data is following normal distribution, because the normal distribution curve includes almost 99.72% observation as area under the curve. Means almost all observation can be used to conclude or to calculate any test or any other empirical distribution, or you can also use in the modeling. Okay, now calculating the probabilities. Now how will you calculate the probabilities? Also you have quite knowledge you have seen in the previous session. Let us see. For more general probability calculations, we have to do the integration. Means integration from minus infinity to whatever the value of x. For the standard normal distribution, we have tables of probabilities already made for us. It is one advantage or one blessing for us. You can say that if z follows normal distribution with 0 and 1, the table for the area probabilities is given. Here, if you want to calculate the area where z is less than or equal to minus 1, so here just see in this column 1 where is situated, and see the difference is 0 because 1.00. So here it is almost 0.1587, you can see. Okay, next, standard normal table. Again, here probability of z is greater than 1.46, then how to calculate? Then calculate 1 minus probability of z is less than 1.46, right? So for 1.46, here select the row of 1.4 here, and 0.06 is the difference, right? So if you will add up 0.06 with 1.4 and just select the value situated over the crossing these two row and columns, you can see it is 0.9279. Nearby the cursor you can see it is nothing but 0.9279. So just this calculation gives that the probability of z is greater than 1.46 is nothing but 0.0721, or in percentage if you want to conclude, just multiply it by 100, so it will become 7.21% of the observations will be area under the curve for probability z is greater than 1.46. Okay. Now question will be there, what if we needed to do a probability calculation for a non-standard normal distribution? Let us see. If we only have a standard normal table, then we need to transform our non-standard normal distribution into a standard one. It means we will have to shift our mean, and we will have to also shift our sigma or sigma square as a variance. So this process is called as a standardization. So let us see. Here standardization formula is nothing but z is equal to x minus mu divided by sigma. Here we convert a non-standard normal distribution into a standard normal distribution using a linear transformation. It is again a good property. If x has n mu sigma square, this distribution, then we can convert to z, which follows n01 distribution. Here each and every observation x will be subtracted from mu and divided from sigma, the standard deviation. Okay, now more explicitly, let us see finding the areas under the standard normal distribution curve in Excel. Because Excel, friends, it is one of the good statistical tool. You can use it as a statistical tool, right? So here let us find out the z value between 0 and 2.34. So it is given as 0.4904. So let me open that Excel. So it is situated over Microsoft Office. Just a minute please. I am going to start Excel. Excel चालू करूँगा. Okay friends, so in Excel you can also manipulate all the statistical tools. You can manipulate mean, variances and all these things. So here we have Excel sheet. You can see. Let me first of all maximize it. Now I think it will be more visible for you. Okay, so we are going to find the values. You can see 2.34. Okay, so I am just writing down the value 2.34. Okay, so this is the value for which we are going to find the tabulated value. So first of all, type is equal to, because in Excel for any formula it is again starting with is equal to sign. So let us see the Excel. Now as you can see, just type, there is a formula NORM DIST and have a bracket. So after typing this NORM DIST, you will be having some definition of that function. So let us see in the Excel. There is NORM DIST. Now here you can see the value of x it requires. Means again you will provide value of x, which is nothing but 2.34, right? Make comma. Now it requires mean. Again, see this protocol of this formula. It requires mean, and mean for standard normal distribution is 0, right? So now just follow this in Excel. Mean is 0, then again comma, standard deviation is 1. So type 1 again, comma, and type true, T-R-U-E, and close the bracket, press enter. So here you are getting 0.99036. Clear? 0.99036. So here this value is 0.99036, means here the 0.5 area of the left hand side of the curve is already included, right? So there is no need to include that 0.5, that is the probability of left hand side curve's area. So let us see again in Excel. You can also calculate the same, again starting with is equal to, click here fx. Fx is a function. So you can see here this dialog box. So in this dialog box, just select statistical function. Here there is a statistical function, right? And now here press N and select NORMDIST. Now click on OK. So you will be having this type of dialog box. Here press X. So here the value 2.34 is situated in the A column and third row. So I'll type here A3. Clear? And mean again is 0, standard deviation again is 1, and cumulative type true. Clear? So here value of X, don't type the value, just type the location. Here 2.34 is located in the first column, which is A, and third row means A3 is location. Here you can see. Now click on OK. So again you are getting the same value but through different way. Okay, here I hope that you know that A3 is location. Here in the formula bar at the extreme left you can see the address of the cell you have selected. Okay, for any cell, suppose I have selected this cell which is situated over A2, so here they will be written A2. Okay, again we are moving to our main slide. So friend, it is very easy to manipulate our all statistical functions in Excel. Here you can see the steps you can write down. First of all, enter the value of X for which you wish to find the normal lower tail probabilities into a cell, say A1. So in our case, we have entered the value in cell A3. Similarly, next step is click on the adjacent cell and click on the function button fx. And next is select statistical function and select function NORMDIST and click on OK. So at the particular cell you will be having the same value. Now if you want to have this probability for different value of X, then you can repeat this for each X value, or you can also use the fill down command in Excel that I hope you know. You can also copy and paste the formula in Excel. If you copy and paste any cell, then it means you are copying the characteristic of that cell instead of any figure you have entered. Okay, Now limiting form property, it is also one of the good property of normal distribution. Here the limiting form of the binomial distribution as n tends to infinity for fixed p is the normal distribution. Let us see. When n tends to infinity, you have a binomial distribution where n is large and p is middle of the road, means p will be near about 0.5, not too small, not too big, but it is more closer to 0.5. Then the binomial starts to look like a normal distribution. Let us see here. Here there is an example. Here the data are collected for transition time. So in colleges you may be having some theoretical lectures, you may be having some practical lectures. So in the theory class you are attending theory lectures, but whenever you are going to perform practical, you are supposed to go to lab. So the time taking you to shift the class from the laboratory, so vice versa, this time has been taken. And let us see the screen. You can follow. Here for n is equal to 5, data is not looking like a perfect normal, but for n is equal to 10, 20, and again whenever you are going to approach for n is equal to 40, it is going to be look like a normal distribution curve. You can see, or you can able to see the curve like a normal distribution, means bell shape. Now for n tends to infinity, now we will take some large number of n. For 2000 students, I have got the time, that transition time, means time to go to the class. It is perfectly like a normal distribution with mean 9.73 and standard deviation like 2.90. Now again let us have one smoking example. Now the data for the smokers have been collected for who are smoking 8 cigarettes, 7, up to 1 cigarette. So you can see for large number of data it is going to be quite normal. Now what is the probability of a fewer than 2 cigarette smokers? So again mu is 4.8 and sigma is 1.39 have been calculated, and probability for less than 2 is again 0.022. This value is obtained from that Z values table. Here we have standardized Z as 2 minus 4.8 divided by 1.39. So it is going to be minus 2. Right? Again one example is there. An unbiased tetrahedral die with face mark 1 to up to 4 is thrown 400 times. So again it is a case of binomial distribution, because here the variable is of dichotomous type. Let us see. If x be a random variable representing the number of ones obtained in 400 throws. So here x is distributed binomial with with n is equal to 400 and probability of success is 1 upon 4. So now we will convert this binomial distribution into normal. So for mean NP, means n and p, multiply this both quantities, you will be having 100. So your mean is 100. And variance is NPQ for binomial distribution. So NP is 100. Now multiply with Q. Q is nothing but 1 minus P. So 1 minus 3, 4. So again it is going to be 75. Let us see. Probability of x which is less than 90 will be again probability of x less than or equal to 89.5. We have used the approximation here, and again convert our x into standard normal variate z, means subtract from mean and divide from standard deviation. So we are getting minus 1.212. And now you know how to look up the Z value table or how to calculate this tabulated value from Excel. So you can use this both the way. 0.1127 will be the answer, means 11.27% is there. Okay, now again just have a look up. Whenever you are going to change mu and sigma, what happens? Here if you will change your mu, the entire curve of your distribution will be shifted over left or over right. If you will change your sigma, the variability of the curve means the spreadness of the curve will be different. It may be quite wider or quite narrow from the actual normal distribution. Okay, here we have a figure where mu are same for curve A and B, means the location of the mu is unchanged, but since sigma is changed, the spreadness of the curve is differing, right? Similarly, in curve B and C, you can see that sigma is unchanged, remains same, right? But mu is different, means the location of the mean is different. The entire curve, the spreadness of the curve will remain same in this case. Here, keep it in mind that each curve has total area of 1. Now, again, most important property, sampling distribution is a distribution of all the possible values of a statistic for a given sample size selected from a population. Let us develop a sampling distribution now. For sampling distribution, now assume there is a population. These 4 are observations of any population. Now here the variable x is 8 individuals. Suppose there are 18, 20, 22 and 24 years respectively. Okay, now we will generate the sampling distribution. So here again summary measures of the population distributions are there. Here mean mu has been calculated, which is 21, and sigma is also calculated, which is 2.236. Here it is a uniform distribution. You can see that probability of all these 4 persons is same 0.4, 0.25. Okay, now let us generate all possible pair of 2 persons. Here ages are given, so there will be total 16 observations, or you can say 16 pair of 2 persons, 18, 18, 18, 20, 18, 22, 18, 24. Similarly, up to 24, 18, 24, 20, 24, 22 and 24, 24. Now, in this case, now corresponding means are given for all the 16 observations. Means here 18 plus 18 divided by 2, 18 plus 20 divided by 2, 18 plus 22 divided by 2, 18 plus 24 divided by 2. Likewise, here all these 16 observations are there. For sample size is here 2, means here we have paired only 2 observations for simplicity for our case. Now developing a sampling distribution using these 16 observations. Here probability of getting 18 among these 16 observations is 1 upon 16. Similarly, 424 is there, 1 upon 16. So here 18 and 24, it is 1 upon 16 is quite here. Similarly, for observation 19 and 23 are repeating 2 times among these 16 observations, so the probability will be 2 divided by 16. So it is again given here in the column chart. Again for observation 20 and 22, you can see they are repeating 3 times in 16 observations, so the respective probability will be 3 upon 16 for each, and remaining is 21. So observation 21 is repeating 4 times among these 16 observations, so probability will be 4 upon 16, which is nothing but 1 upon 4, and again 0.25. Is that? So here you can see again the curve is like a bell shape, which is for normal distribution. So whatever your population, but whenever you are finding out the sampling distribution, again it will be always following the normal distribution, right? Now here developing the sampling distribution. Again we have found the sampling distribution, all 16 observations mean it is again 21 and variance again 1.58. Now compare, let us compare. Population n is equal to 4, here sample size n is equal to 2, mean is remain unchanged, mu of x is 21, where mu of x bar is also 21. We have calculated, right? Here. Okay. Now sigma is 2.236 for population, but here sigma is decreasing. Variability is decreasing. Sigma of x bar is 1.58, you can see here. Now let us discuss normally distributed phenomena. Here the many type of data conform to the normal distribution. Here examples are there. If you are gathering the data for intelligence or IQ scores, it will again be follow normal distribution. Similarly, data of height, weight of human beings or any animal, it is also following the normal distribution. Here weight and length of the fish caught in a large lake or in a sea again will be following normal distribution. Annual incomes of household, set or GRE scores, grades in exams or in large classes, climate and many physiological data incomes will follow normal distribution. Now financial indicators and economic data will not follow normal distribution. Usually the price changes, interest rates, stock values, commodity prices and exchange rates are not following normal distribution. Similarly, lifetime of humans, lifetime of mechanical or electric devices, waiting times in queuing and safety data, for example car crash data, will not follow normal distribution. Now let us have some activities. Skip this portion because we have already discussed in the previous session with our respected Professor Ashok Shah sir. So we skip this example because you know already that. Now activities. Friends, just try to utilize your knowledge, whatever you have studied, try to work with real data. For that, here there are two activities. Look at the 10 centimeter on a ruler and then take a ball of string. And every student cuts a piece of string of 10 centimeter from the ball of string by guessing without using a scale, right? And measuring the length of all the pieces in mm. Now let us see what you can do. Using this activity, you can also describe the distribution of data, whether it is following normal distribution or whether it is right skewed, whether it is left skewed, all you can discuss. And here can we manipulate the data that these factors can be removed, means there will be some factor. If your data is not following normal distribution, there will be some factor. So try to identify that factor and try to remove it and discuss how you can remove and describe the distribution again after manipulated data. And another is, now give some number of matchboxes to all the students in the classes and ask him to count this matchbox sticks for each matchbox. So it will again be following normal distribution with mean and sigma, whatever may be different. Okay, thank you friends. Now if you have any query, your queries are most welcome at any time. Thank you.